up to 6,000 RPM, and it's using the centrifugal force. So this is the easy way to make a even film. Then the next one is the vacuum thermal evaporation. This is actually is a very high vacuum we need it, and this for the small molecules, small organic molecules, which cannot be dissolved or dispersed in solvents. And also it should be can be evaporate, but the maximum temperature we can use at 500 degrees Celsius to heat it up and evaporate from solid to gas. This is very highly accurate method, but economical is not cheaper. Is not cheaper compared to spin coating. And the next one is organic vapor phase deposition. This is not heat like that. They are using that carrier gas and evaporating on the substrate. It is better than VTE and more efficient one. Then the next one, inkjet printing technique one. This is another method of solution processing method. It is it can be print for it's the large screen displays for the TV they use for this one, but vacuum thermal evaporation is not possible for the large screen, large size display substrate, because we can't get the film even thickness even as the whole area. But here in the inkjet printing, it is possible to do it. And also the slot coating, also the same. It can be used for the large areas. And that, but this operational cost, this low operational cost throughout. And the next one is spray coating. Spray coating is another method to make the problem here, but that the distance is dependent on making the size of the substrate. But I'm going to talk about mainly that vacuum thermal evaporation and solution processing, which we are normally used to make OLED and QLED devices. First, we just take one of zinc oxide. How to make one zinc oxide? That zinc oxide we use for QLED manufacturing. So that zinc oxide is working as a ETL, electron transporting layer. We use zinc acetate dihydrate that we take 0.22 gram, 0.1 mole. Then monoethylamine 0.06 gram is 60 milligram, and 0.1 with add with 10 millimeter ethanol in the round bottom flask and reflux for 1 hour. We will get a very clear homogeneous dispersion. We can get it from that. So I'm going to start today's talk about this one. So how we are going to make the thin film and how we are doing the characterizing the thin film, because the film is the important for making these devices. So, right, that's zinc oxide thin film. We made that zinc oxide sol-gel dispersion, then spin coated at 3000 RPM. Okay, we made the film now, but then we need to anneal. Why we need to anneal? We need to get rid of that solvent. To remove the solvent, we're using two methods. One is 120 degrees under vacuum, left it for 30 minutes to remove all the solvent. And the other method, we just put it in furnace. It is not vacuum. Furnace for at 200 degrees, we let it for 10 minutes to remove all the solvent. Then we characterize these films. So this is just that what is the proper zinc oxide, because the resources mostly available, low cost material, non-toxicity, and thermal chemical stability, high transmittance is about more than 90%. So lithography compatible, biocompatible, and electrical resistivity, and that high electron mobility film we can make from zinc oxide. So this is we can control the cost for the manufacturing. So, and also it is available, is mostly available resource in the earth. Okay, now the film we made it, and two film we made. One is 120 degrees annealed, and other one is 200 degrees annealed in AR. So there is a UV absorption plots. You can see this, the red one is the 120 degrees annealed, that high absorption, and this is a little bit low absorption in the when we annealed at 200 degrees. And also the TEM, there is, you can see this both 121 and 221. The particle size, you can see that this around particle size is we get it 5 nanometer from this dispersion. Then this contact angles normally we drop on the drop the deionized water on the film and measure the angle. So when we anneal at 120 degrees, that 28 degrees that contact angle, but 200 degrees 24, so 4 degrees less than that. This another surface morphology, and this thickness we measured using the nano step. So thickness is 48 nanometer, but we use the same solution or same dispersion and same speed, but that little bit thicker film we get at 120 degrees, that is 6 nanometers less. But when we compare with the AFM, AFM, we use the AFM method to measure the thickness, but a little bit more. There are some issues. It might we just make some line or one scratch on the film, and we measure the thickness from the AFM. It might be some error. So this, it says 55 and 48. So we can see that 120 degree annealing giving more or thicker film than this. And we run these two films for XPS and this AFM image. The XPS, the 0-1s region and C1s region, we will see the difference. So the XPS it will help us to find out the homo-lumo position on that. And this AFM image of these two, the 120 and the 200, but when we at 120, the roughness is 1.16 nanometer, but 200 nanometer we get 0.73 nanometer from that. So these are the important things why we did for that thin film characterization for those. Now we will see the quantum QLED devices, how differently we can make the QLED devices. So this is again, I have already talked about, but it's the quantum advantages and those. And this is the conventional OLED device structure. This because OLED is initially started with the structure, so we call conventional OLED device structure always that. So this is, we can do all spin coded. We can do the solution processing, all of them. Here, inverted device tracker, we can do this one, electron transporting layer, which has a zinc oxide dispersion and quantum dots, we can use it. But here we have a problem when we use small molecules. There is some problem there to make devices, because sometimes this wiped out that the previous film when we using solution processing. We will talk about this one later. Now, right. We initially used inverted device for our devices, QLED devices. Why we use that one? Because inverted means we use electron transporter first, then quantum dots, then these layers on the top. The whole electron block, a whole transporting, whole injecting, then cathode. So because that this is well-developed large-size active matrix OLED technology. Most of the display manufacturers, they're using the inverted structure. That is easy to run for that. Easy to run with these transistors. We already talked about it. So they just using this. That's why we try one method. And high efficiency, clear emission, color, and long lifetime due to less quenching effect. Okay, this method, it is possible to reduce the quenching effect. And the ETL, normally we are using 200 degrees to anneal, high temperature. But if we put the ETL top of quantum dots, we are using here quantum dot top of ETL. If we use ETL top of here and annealed high temperature, the quantum dot will be affected, because the quantum dot's maximum temperature, the suppliers always tell us that 80 degrees the maximum temperature we can anneal. Otherwise, it might be that the characteristic of the quantum dots will lose that emitting sites. So this is possible. So we can use high temperature ETL, so zinc oxide or metal dope zinc oxide salt gel method one. We can use it, and we can use any temperature to anneal, because it's not going to affect anything. This top of the ITO. ITO never affected by high temperature. Then that HDL availability, because HDL, we can use this vacuum thermal evaporation, all this, but there are a lot of material available for this electron block, whole transporting layer. We have a lot, because we already made OLED devices. OLED devices are in the market now. OLED device applications are in the market now. So it is so most there are many different HDL, HIL there, so we can use it for if we use this method, because otherwise, if we do vacuum thermally here and put the quantum dots, the quantum dot solvent will disturb these layers. So if we use vacuum thermal evaporation top of any solution processing, it's not going to affect anything, because that's going to be film like a dry film. It doesn't going to affect anything. It's going to deposit on the top of everything without disturbing the previous film. So those are the reasons we use to make inverted device structure for these QLED devices. So this is the first thing we do. If we use the 10 by 10, 10 centimeter by 10 centimeter substrate, I'm just taking the tour about how we are making devices. So first, we just clean the substrate. There are many ways, different people using the cleaning the substrate. If it is good ITO substrate, then you can just start with the rinse with the acetone, then ultrasonic cleaning in acetone for 5 minutes. This ultrasonic, then you can put another container or another put that ITO in with enough acetone and leave it for 5 minutes to ultrasonic. Then rinse with propanol. Then take it out and clean with. You can spray the isopropanol. Then put isopropanol in for 5 minutes to ultrasonic. Then using the deionized water, clean by the deionized water thoroughly. Then put put it in the 5 minutes in the deionized water. Then take it out and try it for 150. If it is 100 degrees, you can put 150 degrees in a vacuum oven for 20 minutes. That all the water will be removed from the substrate, so it will be clean substrate. You will get it. This is the initial bed cleaning for the ITO. So you can try for this cleaning method, or you can use some detergent, Decon 90 for 5 minutes cleaning, and sodium hydroxide, 5% sodium hydroxide concentrated water for 5 minutes. You can do it, then you can continue with. And also it will, if it is some it's not quality ITO substrate, then you can try this method first, then you can do with some organic solvent later. Yeah, we just did make some cleaned ITO. Now I'm going to make one of these device for the quantum dot device with zinc oxide as a ETL, quantum dots as a emissive layer, DCTA as an electron blocker, HTM14, which is whole transporting layer, HCN, 10 nanometer, which is that whole injecting layer. So these three is going to be in vacuum thermal evaporation. So the cleaned ITO, what we are going to do, another cleaning the surface, the ITO surface to be cleaned. So we just going to put in the UV blaster for 10 minutes. Then we just transfer to we have a pre-treatment chamber, so where we can do the oxygen plasma treatment. That would be done for 25 seconds. Then we take that substrate out and do the zinc oxide nanoparticle film. It's the same way we made the thin film earlier. So we just using the same 3000 RPM and make that thin film, and annealed. Here we annealed at 120 degrees for 30 minutes under vacuum. So then what we need to do after this, we can do this is open environment. Then we need to transfer to glove box with the nitrogen purge layer. So this the rate, evaporation rate for this DCTA and HTM14, we used for HCN, we use 0.5 amps per second. So this is all we using amps per second. How it's that film made it in the substrate. So that's the way we found out it's the best 0.5, and the tooling vector we are using for the one. So we must use around 1 Armstrong and 0.5 or to make that right thickness of the film. This is 10 to the power minus Pascal, that vacuum level. Normally this is ultra vacuum chambers. Then we transfer to the cathode. Cathode we use as aluminium. Aluminium we got 80 to 100 nanometers. So we must do it within 3 minutes. So we just the rate between that, we can't get the right constant rate. This is the rate between 5 and 10 Armstrong per second. So it will be done